Hello all, and welcome to this presentation on active learning and how it can be used as a powerful tool for optimization in process development or R&D. But for maximum impact, we need to make it accessible. Quick disclosure statement. I do have a financial interest in the company I'm presenting on behalf of today, but of course the presentation will not be influenced by this. Now, I'll introduce our company, Synthace. We have a cloud-based software platform for helping to design and run powerful experiments and to automatically structure data. And as you'll see, this capability is well suited to helping us run experiments via active learning. Quick agenda for today. We'll first introduce the concept of what active learning is, then go on to show some examples from literature, then go on to discuss work from us and from others in trying to democratize the accessibility of these techniques for the scientists in the lab. I'll then show a quick worked example and then some conclusions. Active learning is a method which depends on building models, so it's always good to remind ourselves of this famous quote from one of the founders of DOE, George Box. All models are wrong, but some are useful. The point, of course, being that the models rarely reflect the truth of the system, but are merely a pragmatic tool which represents our best guess of how the system works. We may be looking to find the optimum, but in reality, we're usually going to end up with a compromise where we find the best conditions, which we find within a fixed set of constraints, be that the number of runs or a number of iterations or just a unit of time which we've allocated to this task. The goal of machine learning is to create systems that can improve their performance at some tasks as they acquire experience or data. And in many natural learning tasks, this experience or data is gained interactively by taking actions. This is not how most machine learning research is done, however, which treats the learner as a passive recipient of data, which is just processed. So you don't have control of what data you end up with. You just build a model based off that data. But the passive approach ignores the fact that in many situations, that's your most powerful tool, is to actually be able to query the system that you're investigating. And particularly in the experimental sciences, we should take advantage of that ability. And active learning is the study of how we can use that ability effectively. Active learning comprises of multiple cycles, or well, it can just be one, but multiple cycles typically of 3 different stages: performing the experiments to gather data, building models to fit to the data gathered, and then choosing the next set of experiments via an acquisition function which takes into account the model and the uncertainty of each of the candidate experiment runs, which we could run next. Now, not all conditions are predicted with equal accuracy and certainty, and active learning typically chooses the conditions with least certainty to investigate next in order to get more data for that area of the design space, which we're not sure about, in order to update the model and move forwards with more confidence in that part of the design space. Showing an example here, we have a Gaussian process regressor, which is a Bayesian model which can be used for active learning. In this case, we're fitting many random functions to the data points which we have so far gathered, shown in black here. The thin gray lines represent each individual function, and the thick gray line represents the mean of all of these functions. The dotted line represents the mean plus the standard deviation. So we can see the red triangle shown in step 1 represents the point at which the standard deviation is highest, and therefore there is the least agreement between the functions. And this is the point at which we have the greatest uncertainty in the system. So therefore it's chosen as the point to which to gather more information on. We gather that information, and then in step 2, we update the model, and now we have a new position which we have the least certainty around, which is shown by the updated the red triangle. A key concept we've got here, which is relevant to active learning, is this concept of explore versus exploit, these sort of two competing objectives. So when we want to explore, we can choose design points that the model is least certain about, as we've shown in the previous example. And when we want to exploit, we'll use the model and choose the design points which are predicted to be optimal for our given optimization criteria or our response. And this is exploit mode. And there's also a trade-off which can be applied between the two. So you can go halfway between the two and then end up with a bit of a compromise between both. And it all depends on what stage of the active learning process you're in and how far away you are from achieving your objective. Now, another example. So we're going to compare Bayesian optimization to a couple of other forms of classic optimization, be that a DOE-based approach, which is conventional RSM or response surface methods, and OFAT, which is one factor at a time. So we'll look at OFAT first in part A. In this example, we optimize the first condition and fix the second whilst we're doing that optimizing the first. Once we've found the optimum for condition one, we can then fix condition one at this optimum and investigate different levels for condition two to find the best combination. This is a flawed approach though, and it's not so widely used anymore in industry, although it's still what's taught in a lot of our schools, because you potentially miss out on important interactions between conditions. The second method, RSM, is a DOE-based approach, where we can test both conditions at the same time and vary levels orthogonally and consistently across the conditions. So we've got each combination being tested. And in this case, we generate more efficient experiments with some partial replication. And also, critically, we can determine interactions between the two factors. And because we're trying 3 different levels in this case, we can actually capture curvature in the system to a basic degree using linear modeling or polynomial-based linear modeling. The final method, Bayesian optimization, shown at the bottom, performs modeling after each set of 2 experiments in this case, and it homes in towards the optima in fewer experiments, but more iterations, and with more dense sampling happening around the optima more quickly. So we're likely to get a more reliable model of curvature around that optima. And really in real cases, it doesn't have to just be 2 experiments done at a time, and for RSM, it doesn't have to be just in one go. You can use a combination of the 2 together for quite effective optimization. And brilliant results can be achieved. So this paper here, they used the Bayesian optimization strategy to maximize mRNA vaccine production. So this is obviously in the days of COVID. And they actually achieved double the yield reported in literature at that time in just 2 hours and in just 60 optimization runs. Another application here shows how it could be applied to metabolic engineering cases as well. So they engineered cells to optimize production of tryptophan. This was done by the Joint Bioenergy Institute. And this paper, which was actually the inspiration for the work we've done in-house, showed where they used a committee of neural network based models in order to optimize cell-free protein expression. And they investigated 4 million, the combinatorial space they were looking at had a size of 4 million compositions, and they needed to efficiently navigate through this space. And they did so in 10 iterations and achieved quite impressive results and a 34-fold boost in yield from their initial starting condition. However, a closer look at the actual GitHub repository associated with this paper shows that there was a huge data burden associated with this. So we actually have 406 CSV files which were generated, and we have 83 Jupyter notebooks which would contain the code in order to perform the analysis and to perform the active learning approach to actually design the next set of experiments in each case. So there are efforts to democratize the techniques, though, to make them more accessible if you are not able to code. So one of these being a tool called ART, or Automated Recommendation Tool, and this was something which was developed as a consequence by the JBay group, which I showed a couple of slides ago. And their tool has a graphical user interface where you can upload your own data, and it can find interactions and suggests next recommended experiments. And another alternative, so there's this tool called Brownie Bee, which was released fairly recently as an open source piece of software from Novo Nordisk and some of their collaborators, where Novo Nordisk actually use these type of techniques in-house, and they wanted to increase accessibility across their organization to the uptake of these techniques. So they've got this no-code ability to apply sophisticated Bayesian optimization and machine learning algorithms but without needing to code. And we also have our own efforts to democratize active learning, which was the inspiration for this talk. Which I'll show you a quick video of that now. So it's a ChatGPT based large language model interface. You can see we use natural language in order to describe the experiment we want to do and the given responses of interest. And we can upload some factors as a CSV. And then the LLM goes about summarizing the experiment. And in the background, it's now building a workflow which can be run in our system and on the actual device of interest. Once it's done that, it will show you a quick summary here. And we can click a link to set up that DOE in our DOE design software. And here we presented, it's pre-populated the conditions which we specified, and it's going to run a space-fill design, present some diagnostics on power to see if we're going to get the required information from the experiment that we're after. Then we'll render the workflows, and we can check previews of those prior to running. If we're happy, we can start the execution, download instructions for our device, which is a Dragonfly. And once we finish the experiment, we'll upload some data and associate it with the plate which was generated. We go back to our chat window now. We can prepare the data by structuring that in the background and again, get a link to run a response analysis. So we'll run some neural net models in this case. So we're running 10 neural net models for each of our responses. And we can see we've got quite good fits there. So in both training and test R-squared scores, we're doing very well, which indicates there's not significant overfitting. And now we follow a new link to go back to the DOE design app. And now we've got an extra tab because it's detected we have an active learning model attached. We're presented with all the potential candidates, and the triangles represent those points which have been chosen for the next experiment. And because we're in exploit mode, it's choosing those which are perform best. We move to explore mode, and then it chooses the points with the highest uncertainty instead. Because it's early on in the optimization process, we go to explore mode and then just repeat the process as before. And on to the next iteration. A bit longer to simulate this time. I won't repeat the cycle. And yeah, this really potentially paves the way for closed loop optimization. The example I've shown here is quite nice because it includes the scientists to sort of validate each of those steps and make any interventions necessary, and to validate that things look good before continuing. And also they get the benefit of being guided through the process as well, so learning about active learning based approaches. So that was quite nice. But we eventually, the real power of this could be in closed loop optimization, where there should be minimal sort of scientist involvement. So in summary, we've got an iterative approach which worked very well and demonstrated consistent improvement over all the iterations. Integrating with our platform actually was very convenient. It sort of lends itself well to our platform's capabilities in dealing with a lot of that complexity and data burden. And we can also potentially look towards minimal user input between iterations as well. It's a sort of pathway to closed loop iteration. The committee of linear models, which we used for that GFP example, worked very well, and it could be nice because it's more familiar to DOE practitioners who tend to use linear modeling techniques. It works well on small data sets and also well with systems which have complex interactions, which we had here. So conclusions are that DOE, Spacefield, AA, ML, they kind of suit different purposes. So DOE can be quite time consuming and subjective and actually needs quite a lot of skill to execute. And this active learning approach promises to be a bit more automatic. So you could speed up iteration cycles there. And the choices we make in terms of whether we use one approach or another, or a combination of the two, can be determined by various factors such as bandwidth. How many runs can we do at the same time? Maybe we can do everything in one experiment in a big space fill, or maybe we're constrained by the number of runs, or it's very cheap to do iterations, so in which case we prefer the iterative approach. And really, the infrastructure for all these techniques is largely repurposable. And multi-objectives are supported. And I think it's very important to support them because I believe they're ubiquitous, really. There's always secondary objectives, which maybe not as important as the primary objective, but are nice to haves and should be investigated in parallel. With that, I'd just like to thank a lot of people involved in doing the work. So particularly Dr. Steve Brown, Dr. Jordan Ang, and Dr. Matt Cooch. Thank you very much.